Math 26, section 1.9, the matrix of a linear transformations. So first thing I want to talk about, when you look in the, if they give us a vector 1 comma 3, okay, so how do you plot it here? So you're gonna go, it's kind of like a point 1 and then 3, so that's the vector. One comma 3. So any vector we have on the xy plane can be plotted the same way. And from the xy plane, we have special kind of vectors here. This is called the I, and this is J. So those I and J, I has components 1, 0, and J 0, 1. Those, we call them unit vectors. So those are the I and J vectors. Any given vector, say V, with 3 comma negative 2, you can write this in the form 3I plus negative 2J, like that. We call scaled vectors. So any vector can be written in terms of the I and J vectors. Those I and J vectors are the basis vectors of xy plane. So basically the basis of the coordinate system. So that's just so you know, when you hear the word basis, that's what it means. So we say the standard basis vectors in R2 only are, you know, the one I showed you, 1, 0, we're going to call it E1. Instead of I and J, we're going to call it E1 and E2, because you will see later we're going to have more than just I and J. Similarly, in R3, we call them E1, 1, 0, 0, E2, 0, 1, 0, and E3, 0, 0, 1. And the question we would like to answer, what are they used for? Well, if, let's say this, if we know what T does, if you know what T does to those vectors, then we can use the information to find out what T does to any vector. And I'll show an example. Let's look at an example. Let T maps R2 to R3. is a linear transformation. Linear transformation means you can use the properties of linear transformation, and that t of 1, 0, 4, negative 1, 2, and t of 0, 1, 0, 2, 3. We would like to determine t of negative 3, 5. So what this is saying, t maps the unit vector 1, 0 into 4, negative 1, 2, and it maps the 0, 1 into 0, 2, 3. They like us to find what is t of negative 3, 5. So t of negative 3, 5. Look what I'm gonna do with this. T of, I'm gonna write it in terms of 1, 0, 0, 1. So it's negative 3, 1, 0 plus 5, 0, 1, like that. Then, since it's a linear transformation, this is like a vector u and this is v, so it's t of u plus v. T of u plus t of v. Another property of linear transformation, it allows me to pull the scalars out. So we take a negative 3 out, t of 1, 0, plus 5 out, t of 0, 1. But remember, t of 1, 0 is given to us. They give us a vector here. Let's see, it was 4, negative 1, 2. 4, negative 1, 2. 5, t of 0, 1, 0, 2, 3. So multiply the negative 3 in, negative 12, 3, negative 6. Multiply the 5 in, 0, 10, 15. And if you add the two vectors, you get negative 12, 13, and 9. So do you see what happened? So if you know what t can do to the 1, 0, 0, 1 vectors, then you can find out what t can do to any vector. That's what I started with the answering, what do we need those for?
Can any linearly independent, like, sort of set of vectors serve as basis vectors?
Yeah, you can say that. So now we notice what the transformations and the basis vectors, how they go along. Now how about if we need to deal with matrices and the standard basis
Before you
vectors.
continue, would you please scroll up?
So we're gonna see how matrices and standard basis vector work together. So if we consider any matrix, say A equals 0, 2, 1, negative 1, 4, 3, 3, negative 5, 0, 0, 1, 6. And we are asked to compute, let's say, compute A times E2. Let's see what we get. If I take the matrix A, 0, 2, 1, negative 1, 4, 3, 3, negative 5, 0, 0, 1, 6, and I want to multiply it by E2. What is E2? Is it 1 0 or 1 0 0 or
It's
well?
I think it's
this
0 1 0.
Oh,
Wait,
this is
0 0 1 0 0.
3 rows by 4 columns, so we have to have four rows. Okay, 4 rows by 1 column, so it's gonna be 0 1 0 0, right? Do you see why like that?
Yep.
So it's E2. So remember, E1 was 1 0 all the way down to 0. E2 it's 0 1 0 da 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 all the way to 0. So it depends how far you have to go down with this. In this case, it's the one goes on the second spot and everything else zeros, but we need 4 rows so these match, so we're able to multiply. So what do we get here is, so we're gonna choose what to do with this. So when I multiply this matrix, this vector, multiply this vector by the matrix. So this is what we can do. We can take the 0 multiplied by the first column, 0 2 1, then the 1 multiplied by the next column, then the 0 multiplied by the next column, and the last 0 multiplied by the last column. Actually, this is -6, -6, -6. And as you can see, all the zeros
Aren't we
will
supposed to multiply the first row with the column?
You can do the same way. You will get the same thing. Yeah, you will get the same thing. But let me finish this first. So all these zeros will cancel out what all these vectors. So that will leave only the second vector, -1 4 3. If we multiply the first row by this column, what do you get? 0 times 0 0, -1 times 1 -1, 3 by 0 0, 0 by 0 0. So you get -1. Next one, this row by that column, 2 by 0 0, 4 by 1 4, -5 by 0 0, 1 by 0 0. So you only get 4. Next one, 1 by 0 0, 3 by 1 3, 0 and 0. So you get 3. And that's what I got here.
All right, sounds good.
We introduce a theorem now. Let T from Rn to Rm be a linear transformation. Then there exists a unique matrix A such that T of x equals Ax for all x in Rn. So if T is a linear transformation, then there exists only one matrix A that T can take x into Ax. Next, so here again, what is A? A is a matrix whose, when you do Ax, A is a matrix whose jth column is T of Ej. So A here, when you write A, we can write it as T of E1, T of E2, T of E3, all the way to T of En, So the jth column would be T of Ej. So the first column T of E1, second column T of E2. This makes A as a unique. This makes A as a unique matrix. And so again, that makes A as a unique. So we can write every linear transformation. Good to keep in mind is a matrix transformation. What's the proof for this? Can we prove it? So two things we need to prove here. We need to prove that T of x gives me A of x for all x. We also need to prove the uniqueness of A. So if we let x taken from Rn and x as x1, x2 all the way to xn, then you can write x as x1 e1 plus x2 e2 plus xn en. Do you guys see why? Let me show you why. So x1 e1 is 1 0 all the way to 0 plus x2 0 1 0 all the way to xn 0 0 all the way down to 1. Because when you multiply x1 by the 1 0 0, you get just x1. If you multiply x2 by 0 1 something, you also get x2 and so on and so forth. So if I want to find T of x, what does T do here? So T of x1 e1 plus x2 e2 plus all the way to xn en. Then T of x, this is x1 T of e1, x2 T of e2, xn T of en. See, I pulled the x's out. Those are scalars, right? They're coming from vector x. So we said that the theorem said that if we have T that maps Rn to Rm be a linear transformation, then there exists a matrix A such that T maps X into AX, and this matrix is unique one. And then we commented more on the matrix. We said A is a matrix whose jth column is T of Ej, if you want to get the jth column of A. And again, as I said, A will be unique, so every linear transformation is a matrix transformation. We need to prove two things. We need to prove that T of x gives me AX for all x, and also we need to prove the uniqueness of A. To do so, we took x to be any vector in Rn with components x1, x2 all the way to xn, and then we rewrote x as x1 e1 plus x2 e2 all the way to xn en. Okay, then I rewrote it just to show you what that means. It means E1 is 1 0 0 all the way down to 0, E2 is 0 1 all the way down to 0, En is 0 0 all the way down to 1. Then T of x is T of x1 E1 plus x2 E2 all the way to xn En. You can pull the scalars x1, x2 all the way to xn out, so you get T of x to be x1 E of T of E1 plus x2 T of E2 all the way down to xn T of En. And what is this? this, what I just got on the right side, is basically A times X. So if you take the matrix A with components, these are T of E1, T of E2, all the way to T of En coming from A. And the X's, X1, X2, all the way to Xn coming from X. So you get exactly what we need. How do we prove uniqueness? You prove uniqueness in mathematics when you consider another vector or matrix, and then you will see that it acts the same way as the first matrix, so that therefore the two matrices are the same, and hence it's a unique. So to prove uniqueness, suppose B is any matrix for which T of B or T of X is Bx for all X taken from Rn. So what do we need to see? We need to look in about this, or as we need that no other matrix B would work. No other matrix B would work. So if we write B1, B2 all the way to Bn for the columns of B, then for each J we have T of Ej is B times Ej. That's a vector, Ej vector. So T of Ej, we know it's Bij. And what's Bij? It's small b times Ej. So you get the same thing. Remember how the columns of A were x1 Ej, or not x1 necessarily, A, let's call it A, Ej. So that proves to us. So the columns of B are the same as those of A. So that proves A and B are the same and A is unique. So no matter what matrix you take, T of Ej is going to produce the same result if it's B or A or any other matrix. Now, some quick conclusions, but doesn't mean the section is over. First one, we learned that the matrix A, whose columns are T of Ej, is called the standard matrix. Standard matrix for the linear transformation. T. Next one, we define any linear transformation by explaining what it does to the standard basis. Vectors. And let me talk about a kind of transformation. It's kind of like a rotational transformation. So if we take the vectors E1, 0, 1 in the xy plane, 1, 0, and 0, 1, we define new transformation that represents a 60 degrees counterclockwise rotation about the origin. So this is 0, 1, E2, E1, 1, 0. So watch what happened when we do rotation of 60 degrees counterclockwise about the origin. What happens to these small vectors E1 and E2, or the standard vectors? Let me show you what happens. Let me redraw this. So the transformation will take a 60 degree angle here. So the E1, it goes up here by 60 degrees. So if you drop a height down here, what happens? I drew it big, like, you know, this is E1. So this is 1 here. So this was the 1, became up there. And this is the 30, 60, 90 triangle. If you guys remember, 30, 60, 90. If this is x, this is 2x, x root 3. Special right triangle, 30, 60, 90 triangle. So this is 1, this is 1/2, and this is root 3 over 2. So this becomes here 1/2 comma root 3 over 2. This means 1, 0 became 1/2 comma root 3 over 2 when we apply this t transformation. So this, what we got, this is t of E1, and we do the same thing. This is, say this is E2, you do it 60 degrees, rotate it 60 degrees. This is 30, this is 1, this is 1/2 root 3 over 2. This becomes negative root 3 over 2 comma 1/2. Okay, that's t of E2. So again, what t did to 0, 1, it transformed it into negative root 3 over 2 comma 1/2. Again, if you remember, A can be written always as t of E1, oops, no comma, t of E2, all the way to t of En. And what we got here is what t did, it transformed E1 into 1/2 root 3 over 2, E2 into negative root 3 over 2 and 1/2, and the x stays the same, because what t is doing, taking the vector x into ax. So that gives me the matrix A. and I can show you in general what happens. In general, a rotation of angle, call it phi, phi, angle phi about the origin, counterclockwise, can be represented by the matrix transformation. T of x equals cosine phi, sine phi, negative sine phi, cosine phi, and x. So phi can be any. And so what this does, this helps to rotate any given vector about the origin with the given phi. So this is just kind of like an application to what we have been working on today. The last part in this section is about functions, where you need to know what does it mean to say one-to-one, and what does it mean to say, or surjective, what does it mean to say one-to-one, injective, and onto surjective. So I will post the notes where you can read more about them, the last part of this section, and plus the recorded video, and I will upload also this recorded video for these two sections that we covered today to Canvas.